We are going to begin our plenary session, and it's a great pleasure for me to introduce the plenary speaker, Adélia Sequeira, Professor of Applied Mathematics at the University of Lisbon. And Adélia has an exceptional academic record with many prestigious prizes and awards, and the last one was Copernicus Prize from Italy, and before that a medal from Czech Republic and many others. And Adélia coordinates and leads many programs and groups and projects. I will not enumerate all of them here, but from the scientific point of view, Adélia studies a wide range of questions in applied mathematics and in mathematical modeling. It's like a statistics of collective behaviors. There are always people who are late. So, and in particular, hydrodynamics and blood flows, including non-Newtonian fluids, both from the mathematical point of view and from the point of view of modeling, and many different questions related to that, like blood coagulation and cardiovascular diseases. By the way, not very much represented here, much less, for example, than cancer modeling, but still there are 2 or 3 sessions devoted to atherosclerosis and related questions. So again, it's a pleasure for me to introduce the plenary lecture, Recent Progress in the Mathematical Modeling of the Early Stages of Atherosclerosis.
Okay, so I hope this will work. So good afternoon to everybody. Thank you for the organizers, Marcus Holland, for inviting me, Vitaly for proposing me to come here. It's a big pleasure. It's not the first time I am in this kind of conferences. I have been 2 years ago in Sweden. And in 2 years from now, it will be in Lisbon. So you are all invited to come to Lisbon. In fact, there were at least 2 mini symposia about atherosclerosis, not too much in such a big conference. I decided to keep this title. Nevertheless, there was a talk of my student, Thelma, on exactly this topic on Monday. But so there was not many people attending the lecture, so I will repeat a part of this at the end of my lecture. But I decided to keep the title anyway. So my collaborators joined this, concerning this title, is joint work with Willy Eger, Maria Nelson Radu, Thelma Silva. They are all here. This will be the second part of my talk, in fact. But everything I will say before is related to this. And at the end, in fact, I will repeat a little bit. Okay. So thank you for being here, because this is after a long week of work, after the conference dinner, the walk around the castle city, and so on. So I'm very happy that you are here. So now, this research is done in the framework of 2 projects. I had several before, but these are still running. This one is with medical doctors in Portugal. All of them, in fact, involve medical doctors, and in collaboration with my co-authors, and also Alfio Quarterone and Antonio Fazano, and a second project with Tom Hughes on this MRI-based computational modeling of blood flow and nanomedicine deposition. So this is, I will talk a little bit about this, in fact. As Vitaly was saying, I work on different topics. All of them are quite related, in fact, and involve somehow blood coagulation and atherosclerosis. So I work on mathematical modeling and simulations in cerebral aneurysms. I will talk a little bit about this here. This I will not talk about. The electromechanical modeling of the heart, blood coagulation, I will not talk about. So this is the subject of the lecture, the main subject, in fact. So we also, this is the subject of this project with the University of Texas at Austin. I will talk about this. This is patient-specific numerical simulations for bicuspid aortic valves. We have also worked in this field. And the reducing uncertainty in blood flow simulations using data assimilation techniques. We are very interested in this subject, in fact, because if we want to do patient-specific simulations, we should get good images, and we should get all parameters we need from the medical doctors to run the simulations. And in fact, they don't give us exactly the parameters we need. We need boundary data, and they give us images and not the boundary data we need for the simulations. Because of course, if we want to do simulations, we need to cut the domain, and we need to impose appropriate boundary conditions. And they don't give these boundary conditions or all the parameters we need. And so there are techniques of optimal control, optimization, and the so-called data assimilation techniques that we are developing in our group. Okay, so now concerning atherosclerosis, so this has been repeated in this mini symposium here. So we know that it is an inflammatory disease. In fact, the main risk factors is the endothelial dysfunction and the high concentration of LDL, cholesterol, in the blood. Then, when does the atherosclerosis, the whole procedure starts? When there is important contribution of hemodynamic factors, because it is in the regions of large renal numbers and lower wall shear stress that the atherosclerotic lesions occur, and it happens mainly in large and medium-sized arteries, like the abdominal aorta, coronary arteries, carotid bifurcations, etc. So the consequences, we know that: vessel narrowing, heart attack, stroke, and it's a big problem because then there is also the formation, the plaque can rupture, there is the formation of clots, and this is, you know, it's together with cancer. Even the cardiovascular diseases are the main cause of death and mortality and morbidity in the world. So all this is related, in fact, and that's why I'm talking about now the stents, balloon expandable stents, how to treat atherosclerotic plaques. What the medical doctors do, in fact, is a possibility, is to introduce a stent, to a balloon expandable stent. I have a film, a kind of, where you can see how it works. The problem with the balloon expandable stents is that there are two kinds of stents: the endovascular, the biodegradable, and there are also the drug delivery stents. In fact, the endovascular stents, they restore blood flow, they avoid elastic recoil, they track injured flaps, maintain lumen until healing. And the biodegradable stents, the problem is that there is a restenosis that happens after some months. And that's why the drug delivery stents are used nowadays. And there is a big industry around the stents, not only so the shape, concerning shape optimization, but also the material that is used for drug delivery. I will talk a little bit about drug delivery, but not in the stents content. So what we do numerically, so we do, for instance, if we have an image of a stenosis, like here in the carotid bifurcation. Okay. Then if you introduce a stent, you get this image from an angiography before and after the stent placement, and you get this. So this restores the form of the artery and the blood flow. But in fact, after some time, there is restenosis, and so the problem needs to be solved in any way. So concerning the numerical methods, there are several numerical methods to deal with this. What we do is from the medical images, we do the medical reconstruction, we create a geometry, then we do the mesh, and we run simulations with appropriate models for the blood and for the artery, and if we want to do fluid structure interaction, we do it, or otherwise we can also consider that the wall is rigid. This is a mesh appropriated for finite elements, but you can use finite volumes and other methods. Okay, and then we run the simulations, we obtain some hemodynamic parameters and compare the results. Okay. So now about aneurysms, cerebral aneurysms, atherosclerosis. Cerebral atherosclerosis is also related with the aneurysms. So this is a gradual dilation of arteries, arterial segments, and there are two factors associated with the increased risk for development of cerebral aneurysm. This is essentially the asymmetry of circle of Willis and the cerebral atherosclerosis. This alters the geometry of the vessels. And so here you have a cartoon where you can see the polygon or circle of Willis with several several aneurysms. You can see here an aneurysm. This aneurysms in the brain, they are saccular, while in the aorta, they are fusiform, and you will see a picture immediately. So the vessel stretches and becomes thinner, and they can rupture, causing hemorrhage. And so you know that also this is a problem, and so the patient can die if it is not treated. This is difficult to detect because the medical exams are invasive, and just by chance they can observe that a patient has an aneurysm, and usually if he has he or her or she has an aneurysm, they in general have more than one. And it depending on the form of the aneurysm on the neck, they can be clipped, they can be coiled, and if they are coiled, they introduce still a stent. The idea is to avoid the blood to flow here, and we want to avoid the rupture of the aneurysm. So this is what the medical doctors do. And what can computational fluid dynamics can do to help the medical doctors to solve this situation? We can, in fact, provide images of using appropriate models from the medical images. We do the image processing, the geometry reconstruction, the meshing, running the simulation using appropriate models for the blood, for the structure, and then we can derive, for instance, directions of the flow, and obtain values of the wall shear stress, and indicate and can give indications to the medical doctor if the aneurysm will rupture in one direction or the others. Of course, this is something we are doing in our group, and I forgot to say that in all these subjects I talked about, we have master and PhD students that some of them finished, others are finishing PhD theses, and so all of this is in progress. And so here we are deriving a good model for the wall, and to couple with a model for the fluid. The model for the fluid, we know what it is, but for the wall it's more complex because the wall is damaged, and so the medical doctors, the surgeons, they get a piece of tissue, they do the study of this piece of tissue by hematologists, and they give us the data, the parameters, then we derive the model, and then we are doing this by, let's say, putting in parallel the simulations and experiments. So this is just to give you some hint about this. So aortic aneurysms are also due to hardening of arteries, due to atherosclerosis in particular, genetics, aging, infection, injury, inflammation. They have this form, and usually the medical doctors, either they do the surgery, they cut, like in the cerebral aneurysms. In that case, the neuroradiologists, they treat them, the neurosurgeons, they cut. But so here, they also can cut or then introduce a stent. The problem here, this is some work I am doing with people in Ferrara, with surgeons there, is that they realize that all patients, or almost all patients, that they are treating with stents, after some months, they need to be treated again. So the stents are not doing a good work, let's say, after a reasonable time. They were expecting at least that this could stay stable for a few years, but it's not the case, and they are changing the kind of stents they are using, but it's not the problem. It depends on the form of the aneurysm and so on. So now the other work we are doing is with the people in Austin, is the peripheral arterial disease called PET. So it's the progressive formation of atherosclerotic plaques in the arteries, in the extremities, so in the limbs, head, kidneys, and stomach. This blockage can lead to impaired leg function, reduced quality of life, and possible loss of limb. So this is an early marker of stroke and heart attack. So the treatment, again, is using a stent deployment, so it can be also pharmacological, lipid-lowering treatments, or then vascular surgery, or both. And so in this work, what we propose is something different. What we are proposing here is, in fact, a nanoparticulate drug delivery treatment. So what we do is, by doing some numerical simulations, we detect the region of disturbed flow. We know that the accumulation, so the LDL accumulates in the region of very low shear stress, and accumulation is generally higher at the sites of disturbed flow. And typically, we observe the higher vascular wall permeability and the overexpression of cell adhesion molecules. So then, after determining the determination of the local flow field, to predict the occurrence of the disease and the outcome of the clinical intervention, so this clinical intervention can be the stent deployment or then this one. So this is done clinically and also with the help of the numerical simulations. And this is what we do. So this is the main objectives, is patient-specific flow analysis before and after stent implantation, explore target nanoparticulate delivery to the stenosis region, developed an MRI-based computational protocol that can be used to analyze data from clinical trials and explore possible correlations between hemodynamics and disease progression in PAD patients, and develop a 3D isogeometric analysis based course to model plaque growth and regression. So it could be finite elements, but this isogeometric analysis is more appropriate and gives more reliable numerical results. And so we are using the 3D isogeometric analysis. So this work has been started in another project that we had in collaboration with Austin, and it's still in progress, and so we are now collaborating with them again to see the plaque growth and regression using these nanoparticulate delivery. So here we can, so this is the image-based patient-specific modeling. So this is the baseline, we call baseline. So the images that we get from, so this is a superficial femoral image of a SFA, superficial femoral artery. And these are the MRI images of a patient that, and he has a peripheral arterial disease. So he has a PAD, it's a PAD patient. After then we are following this patient, and after 24 months, so it means 2 years of introducing a stent, then we run simulations and can compare the hemodynamics to see what happened. So here you can see. Yeah. So here, so this is the problem setup and solution strategy. So in fact, so what we do is to couple Navier-Stokes equations for the fluid and advection diffusion equations for the particle transport. Here we consider a rigid wall. This is reasonable because we introduce a stent, and so that is the wall becomes rigid. We could also consider blood as a non-Newtonian fluid, but in this kind of artery, so you know that blood is a non-Newtonian fluid. It depends, but it depends on what we cannot consider blood. We cannot model blood in the same way in all the circulatory system. In the large arteries, blood can be modeled by the Navier-Stokes equations. In smaller arteries, we should take into account rheological behavior of blood, in particular the aggregation and the permeability of the red blood cells, and taking that into account, so blood is shear thinning. But you can also consider the viscoelasticity of blood. and still consider a non-Newtonian model, homogeneous non-Newtonian model for small, so for medium-sized arteries. If you go to the capillaries, so the model is completely different because you cannot have an homogeneous model for blood in the capillaries. So it's not the case here. We are not in the capillaries. We are working with a large artery. So the blood is modeled as a Newtonian fluid by the Navier-Stokes equations, and then we use an isogeometric analysis to run the simulations. So this is the inflow conditions. So this is patient-specific, and inflow conditions are extracted from the data, patient-specific data. Now, I think I have a movie here. Let's see if it moves. So this is the flow analysis before and after the stent implantation. So this is the before, and this is after, 24 months after the stent implantation. So you can see the streamlines. So, and this is, it's marked here, the region of the stenosis, and here you have also, so I was marking in the computer so you don't see. So here is the region of the stenosis, and here is the location of the previous stenosis that doesn't exist anymore. Okay, so now here you can do some transversal cuts and see what happened in these for these different times, A, B, and C. And so you can see that after 24 months, so this is a scale for the velocity magnitude. So the velocity magnitude increases, the vessel is larger, and so you can see what happened after 24 months. Now, concerning the wall shear stress. Concerning the wall shear stress, there is an increase, so for the blood flow rate first, there is an increase of 500% post-interventional, and we can see a much more, here is, this is not very homogeneous. You can see different values of the wall shear stress. Here it's much more homogeneous. And so the flow rate increases by 500%, and the total average wall shear stress reduces 22%. The wall shear stress reduces 40%. So these experiments, numerical experiments, were important to determine the hemodynamic parameters that and then the location and what was the effect of introducing a stent in this PAD patient. So this is the special distribution of OZ. This is for the OZ number. The OZ number reduced also in 32%. And here you can see that here you can see in these plots, you can see, I don't see very well from here, but so you can see that the receptor VCAM1, so it's the receptor VCAM1 density as a function of the wall shear stress. And you can see that the VCAM1 is much, among the inflammatory vascular molecules, VK1 provides the highest accumulations in the stenosis site, because the stenosis site is in this region, and so the VCAM1 is here. So it is much higher than the others. So this means that, so if you want to to use the nanoparticles for the regression of the plaque, the VCAM1 should be the molecules that we use, we should inject the nanoparticles. So this has been done, and the nanoparticles have been injected in a simulation of 10 cardiac cycles, about 10 seconds, from a bolus here placed at the inlet. Okay, then, so this is a cartoon where you can see you can see here what is the form of the vessel and what is the form of the nanoparticle with these ligand molecules in green, the polymer chains in violet, and the drug imaging agents in red. So this cartoon. So what the idea is to, yeah, you see here, cannot see it. This is the endothelial layer, yeah, and so they will be directed to the endothelial layer, to the region where the VCAM1 is higher, and with the nanoparticles. So the idea is, in fact, to destroy the VCAM1. So there is a movie that you can see on the web that has been produced in the framework of our previous project on YouTube. It's called Like This. And this is the address of the movie. I will not show the movie here because it takes 14 minutes. When you can see how this system works for the treatment of the vulnerable plaques. So the preliminary conclusions is that we obtained some hemodynamic indicators within the SFA observed post-intervention by the stent, the use of the stent. And so the blood peak flow rate increased by 500% approximately. The OSI number decreased. The total average wall shear stress and the wall shear stress decreased also, one 22%, the other 40%. And so we observe also that the nanoparticles target to inflammatory vascular molecules, including VK1, accumulate preferentially in the region of the stenosis, in the SFA baseline configuration, so before the implantation of the stent. And so that this selective deposition of nanoparticles within the stenosis could be used for the non-invasive detection and treatment of plaques. So there is, we can see here that there is a possible correlation between hemodynamics and the disease progression in PAD patients, and that this can be used to treat the PAD patients instead of using a stent or of doing a surgery. So to use the nanoparticle delivery. So there are some publications that have been done, so essentially by Shaoli Hossein, Tom Hughes, and co-authors. And there is one in our group where we are modeling the plaque growth and regression using this framework of the isogeometric analysis. So what we are doing here is, because they don't see the plaque growth, they have the plaque already formed, and they are destroying the plaque by the nanoparticle, with the nanoparticles. So what we are doing is coupling the plaque growth with the drug, the nanoparticle delivery. And so this is a work in progress, which is so it will be published. Okay, so now let's go to atherosclerosis more in detail, because we have been talking about atherosclerosis, and part of my time is gone. So the structure of the vessel wall is very complex. Everybody knows that. And we can talk about mechanical interaction with the blood or biochemical interaction. But biochemical interaction is the one which both are important when we talk about atherosclerosis. But we cannot neglect the mechanical interaction as well. So everything happens in the intima layer and the coupling between the intima and the lumen, so at this level. And the endothelium is the layer, the surface that separates both. So what happens, this is a repetition of what has been said before in this mini symposium, but I will say again here very quickly. So what happens is that the LDL enters the intima and becomes oxidized. So then this is due essentially to endothelial dysfunction and the increase of its permeability. Then the endothelial cells, they send signals to the circulating blood, the immune cells, to the monocytes. The immune cells are recruited to fight the unwanted substance, the oxidized LDL. And once in the intima, the monocytes are differentiated into active macrophages. Okay. Then, so this is called, going back, this is called the first stage, so initiation and inflammation. Then there is the so-called lipid accumulation. What happens is that the macrophages, they absorb the oxidized LDL in the intima by phagocytosis process. This reaction transforms the macrophages into foam cells, which are lipid-laden cells, that should be removed by the immune system. And there is a pro-inflammatory signal that contributes to recruit new monocytes. And then there is an auto-amplification phenomena that occurs, and this is a chronic inflammatory reaction. We call that becomes a chronic inflammatory reaction. So this is the lipid accumulation, and then the plaque grows, and so the plaque starts growing and forms a cap. The inflammation process involves the proliferation, growth, so in proliferation, you know what it is, and the migration of the smooth muscle cells to create a fibrous cap over the lipid deposit. The fibrous cap changes the geometries of the vessel, of course, and so you can see the formation of the necrotic core, the macrophage accumulation, the fibrous cap formation here. And so this change the properties of the blood flow of the lumen. The lumen deforms, okay? So then the final step is the plaque rupture, and fortunately not all plaques are ruptured, but it can happen. They are called the vulnerable plaques. And this is due to several reasons, so to local blood flow, smooth muscle cells apoptosis, or endothelial cells apoptosis. And this leads to the formation of a blood clot in the lumen and the obstruction of the artery. And so this can lead to the heart attack or stroke. So I already talked about this, and you can see here in the cartoon what happens. So an hemorrhage, and also the blood clot in the case of formation of the clot. The clot can go to the brain, for instance, and can have an hemorrhage, a stroke. So I like this scheme because here you can see more or less what we have been talking about, and this summarizes all the stages. So initiation and inflammation, lipid accumulation, plaque growth, and cap formation and plaque rupture when it occurs. Concerning the mathematical modeling, of course, you know that it's impossible to have mathematical modeling for all these stages. And there have been, along the years, many contributions, and I'm afraid I will not quote all the authors. In any case, I will quote some of them. So in any case, a model for the whole process of atherosclerosis is impossible because you see that there are several time scales here. So the LDL, so the monocytes transmigration, the behavior, the transport of monocytes, all the transformations at the early stage of atherosclerosis happens at a certain time scale, and the formation of the plaque can take months or years. And also, so the blood flow also takes place, and you know that so these time scales are completely different in order to create a model that takes into account all that. So in any case, if we think about models, they are complex systems of PDEs, of flow, transport, chemical reactions, interactions of fluid and elastic structures, if you make the fluid structure interaction, movement of cells, coagulation, and growth process, additional complex dynamics of the vessel walls. So for the early atherosclerotic lesions, initiation and inflammation, I quote here the work of Nader, Genes, Volperson, so two of them are here, 2007, 2009. This concerns essentially the inflammation, 1D and 2D models, based on reaction diffusion equations that describes the initiation and the self-accelerating inflammatory process. Then for the second stage and third, the inflammation leading to the plaque formation and growth, there is the work of Calves, Raul, and other authors, so 2009, 2010. Silla is more recent, 2013. So this includes the inflammatory process with the penetration of the LDL in the intima and the oxidation due to the action of the wall shear stress. And you can read here. So the areas with lower shear stress, we know that correspond to higher. They consider already that in this model. And this consists in a coupled system of reaction diffusion equations with to model the inflammatory process with the Navier-Stokes, incompressible Navier-Stokes equations for the blood flow with appropriate boundary initial conditions. But in fact, the early stage of atherosclerosis has not been completely modeled, and this is what we propose. In fact, so for the plaque formation, that is the work of Howe and Friedman. I met him a week ago, Avner Friedman, and I asked him if he has something more about this, and he said that no, now he is working on abdominal aneurysms related to atherosclerosis, so he's not now developing more of this work, because I asked if he has something in 3D, but he doesn't have. So but it takes into account also the good cholesterol and so the interplay between LDL and HDL in these models. For the plaque growth and calcification, we have the work of Young, Willy Jäger, Maria Neus Radu, they are all here, and Richter, evolution of a 2D plaque with numerical simulation based on finite elements, and we had a talk on this the first day. And now there is also some work concerning FSI model for atherosclerosis by Nader, Walid, Vitali, and Sumaya, 2009, 2014, 2016. So, and there is much more. So I'm sorry, I will not say the work of everybody. Now, concerning the early stage, so concerning the early stage of atherosclerosis, for the early stage, we mean the initiation and the inflammation. For the initiation, the initiation includes the LDL in the bloodstream, so in the lumen, the LDL on the endothelial surface, then we include the endothelial permeability to LDL due to wall shear stress, and the LDL all on the endothelial cells, the LDL in the intima, and the oxidized LDL in the intima. So this is the initiation. And then the inflammation, so the cytokines in the intima, monocytes in the bloodstream, monocytes on the endothelial surface, endothelial permeability to monocytes due to the wall shear stress and the cytokines, monocytes in the intima, macrophages in the intima. So you see that already for the initiation inflammations, this so-called early stage, there is already a lot of ingredients. So for the blood flow model here again, we consider Navier-Stokes equations with appropriate boundary conditions. This is a portion of a vessel with so this the inlet and the outlet, the vessel wall. So this is the intima. Omega I is the intima. Omega L is the lumen, where the blood is flowing, and so this is the media here. Okay, so we have appropriate boundary conditions. So we consider Newtonian. And so for the intima layer, we give also some equations. So we consider the intima as a quasi-static biosystem, because we consider that intima is a poroelastic medium, and these are the equations for the intima layer, for the biosystem. So omega eta S is the displacement of the porous solid with respect to the reference configuration. Pi is the pressure of the poroelastic medium. And then these are two Lame coefficients, one for the compression, the other for the distortion. And then we have also boundary conditions here. So this is coupled with the fluid. With the Navier-Stokes equations, we impose continuity of the normal flux, the balance of the total stress in the fluid phase, and the no-slip interface condition for the tangential component of the velocity field. So this gamma I is the porosity of the medium, and K is the conductivity related to the permeability of the medium. Okay, now we have a series of equations that I will pass very quickly. Okay, so very quickly, in fact. So transport of LDL particles in the lumen. So I will pass really very quickly because this was already done in the first day. So presented in the first day. So in the lumen, so we have advection diffusion equations with boundary conditions. This is for the total flux across the endothelium. So this includes the permeability of the endothelium to LDL, which is a function of the wall shear stress. And this is important to consider this function and of the concentration of LDL and endothelium. Then for the transport of the LDL particles, we have also the transport on the endothelium surface and the LDL in the intima. So this factor here represents the accumulation rate of the LDL on the endothelium surface. LDL in the intima, we have a diffusion coefficient here. Then the velocity of the flow in the intima is included here, and this is the oxidation rate with appropriate boundary conditions. Now, for the chemical transformations of LDL. For the oxidized LDL in the intima, we have these equations. LDL quantity, this includes the LDL quantity phagocyted by macrophages with these boundary conditions. Equations for the cytokines, MCP1, concentration in the intima, the boundary conditions, so transmission and boundary condition. And for the transport of monocytes, so you can imagine that then if we want to do some simulation, we need to simplify the model somehow, because there are a lot of equations, lots of parameters here. So then the transport of monocytes in the lumen here with these boundary conditions. This FM represents the production of monocytes due to the FIM, which is the factor increase in monocytopoiesis concentration. Okay. Now, transport of monocytes. So the endothelium surface. Wow. So I have 2 minutes, so I need to run. Okay, let's pass. Transport of monocytes, and then macrophages concentrations, foam cell concentrations, and these equations. Okay, now numerical simulations. For the numerical simulations, we were obliged to simplify the model somehow and to eliminate the FIM concentration, for instance, the influence of FIM, and the BO equation, the coupling with the BO equations. So these are the blood flow, velocity, magnitude, and streamlines. We consider 2D simulations for this simplified model. So in fact, coming back just to see, this is not a plaque which is already formed. This was a deformation of the vessel wall, just to be sure that here we will have a decrease on the wall shear stress, and then the formation of the starting formation of the early formation of atherosclerosis in some place here where the wall shear stress is lower. And we can see in this graph here the spatial deformation of the wall shear stress along the stenosis vessel, that this is the region where the wall shear stress is smaller, is lower, and so it's in this region that the plaque is going to start forming. The endothelial permeability to LDL as a function of wall shear stress. You can see the graph here. And then you have here also some plots that we obtained, evolution of LDL concentration on the endothelial surface as a function of the wall shear stress. Then you can see for different times, it's increasing, the LDL concentration, and you can see this for 2,000 seconds, how it behaves. Now, I have a movie later, but not now. So this is for the cytokines concentration and the zoom view, because you see this is the region of the lower wall shear stress. It's the region of the early atherosclerosis, where we have the formation of the plaque, the starting of the formation of the plaque. This is a zoom. Here we have endothelial permeability to monocytes as a function of wall shear stress and the cytokines. So you can have also this plot, and now this is a movie. I hope it will move. So you don't see much here in this one because it's very narrow. But then we will do a zoom immediately, and then you can see better. And when you do the zoom, then you can see what happens. And in fact, you can see that the monocytes concentration in the intima is growing in time. Okay. Then this is for the cytokines concentration with a zoom. And then we have a movie here where you can see how it behaves. It takes some time, but it will come. This is, as you can see. So this is the region where we made the zoom in order to see something. Okay, now these are some publications that we have in this framework. And now I want to thank, these are not all my collaborators, but are the collaborators to the part of this work I presented more in detail. So Willy Jäger, Maria, and Thelma. So Thelma did the simulations and the last part of the work, so in collaboration with Willy Jäger and Maria. And so this is Shaoli and Tom Hughes, with whom I work at UT Austin. And we don't see him very well, but this is Jorge Tiago, is my postdoc, who is involved in all the work I'm doing in my group. So thank you for your attention.
Yes, thank you very much for this very interesting, very important presentation. And unfortunately, these problems concern all of us here, or almost. So are there questions?
There is one question.
Yes.
I'm sure you are all disturbed with the cardiovascular diseases, for at least older people, not young.
No, by the way, no. Now it concerns even small babies.
Small, even children.
Unfortunately, it's like that.
Yes,
so life progresses now. Everybody's concerned.
So, in your simulations, you had the plaque forming in about 2,000 seconds. So I think a lot of doctors would think that plaques typically develop on the time scale of decades. So what do you think is the main process or processes that are responsible for making the development of plaque so slow?
No, this is the early stage. So this involves only the process of, so the LDL penetration, the formation, the starting process of the plaque, not the formation of the plaque. So then the whole process repeats itself, and then up to the formation of the plaque, it takes too much. It takes months. It takes years. So and it starts growing slowly, but the process it's quite fast. You know what happens in our blood vessels if we have high blood cholesterol, if we have endothelial dysfunction. In fact, this process starts, and it starts quite fast. So this question of time scales is very important, and if that's why it's not possible, so perhaps it's possible, but we still didn't do it, and I think it has not been done, to create a model that takes into account the different processes from the beginning till the end, till the formation of the plaque. People is considering the plaque started and it's growing and interacting with the blood, and then there is no plaque and it's starting, and it's our case. Then what I showed in the deformation, it's a deformation of the vessel just to create a low wall shear stress in some region of the vessel. It was not, this was in fact an idealized vessel, and we are interested in doing patient-specific simulations in real images.
I would also add that our organism has several mechanisms of protection against that, so it's constant interplay between the disease and protection, so this is why it can take more time. So please...
the process of oxidation of the LDL is also quite complicated, right? That can occur in multiple steps, and that might slow down.
Yeah, of course it is not, there is protection against oxidation in blood, but not in Intima, so it's quite complex. Yeah, please, other questions? Yeah.
Yes, thank you for a very interesting talk. My question has two parts. The first one is, you want to be really patient-specific, so you take that inflow condition to the artery from the MRI data. But we all probably know that my blood, how my blood is being pumped, depends on what I ate during the morning. It depends on if I'm standing or lying, so is it proper to draw any conclusion from a very particular inflow condition? And also, for the second part of the talk, I'm curious, you're interested in the wall shear stress, but you don't consider the elasticity of the vessel. I understood that assumption with the stent, but if you're modeling a healthy artery, why you're not considering the elasticity that reduces the wall shear stress to some extent?
So concerning the first questions, can you please repeat? You said that it depends. So if we are considering patient-specific the inflow conditions, it depends on what? I didn't hear.
So the inflow condition depends on the heart rate, on the cardiac output.
Yeah, sure.
So drawing conclusion from comparing two profiles from different inflow conditions, does it really tell us
no, that's why it's patient-specific. So we can derive conclusions for this patient. Then we can do simulations for other patients, and then do a kind of statistic analysis and conclude obtain some results. So the fact that we conclude, and it depends on the state of the disease. So we are talking about the PED patient. So in the case of the PED patient, it depends on the stage of the disease, if it is advanced or if it is in an initial state. So, and the inflow conditions, it depends. So we take as I said, for instance, the medical doctors usually, they don't provide the initial conditions and boundary conditions exactly where we want for to run the simulations. We should derive them by doing some data simulation analysis and using optimal control methods. And so we do that, and since it is patient-specific, it's for that patient. We cannot derive in general. But
blood flow, for example, you do the OC numbers, some indices comparing to flows, but for example, if the patient stands up, the flow reduces because of gravity, because you're constantly in cerebral flow, and it has been shown that the flow is then reduced. Maybe those two numbers won't be that different and won't have any prognostic value.
Yeah. And in the case of PED, you need also to take into account the fact that there are involuntary movement, involuntary motion, and then the data is not very reliable.
Yeah, I suggest to continue this more detailed discussion after that. And also, your second question was about elasticity. In fact, Adélia didn't answer, but there's a lot of studies about fluid structure interaction.
The second I didn't...
It's about wall elasticity. You briefly mentioned about this fluid structure interaction. There are many studies of that, so it's... Okay.
Yeah. No, here I didn't consider the elasticity. It was just at the level, cell level, so the LDL and oxidation.
Probably no, then thank you again.
Thank you.